All right, in this video, we're going to talk about section 10.2 dealing with regression. In the last video, which was section 10.1, we talked about correlation. And then we're going to look at regression in this section. Then we're going to use paired sample data to find the equation of the regression line. And also we're going to find the best predicted value of a variable given some value of the other variable. Okay, so what we're going to be looking at is methods of finding the equation of a straight line that best fits a scatter plot of the sample data. And the best fit straight line is called the regression line, and its equation is called the regression equation. And here we can use the regression equation to make predictions for the value of one of the values given some specific value of the other variable. Okay. All right, now let's look at some basic definitions here for regression. If you're given a collection of paired sample data, the regression line, which is also called the line of best fit or least squares line, is the straight line that best fits the scatter plot of the data. Now, we did talk about what a scatter plot was. It was a graph of paired XY data. Now, the points don't necessarily have to be a straight line. They can be a set of points where, it can get close to a straight line. Now, the specific criterion for the best fitting straight line is the least squares property described later. And the regression equation is going to be y equal b sub 0. Y hat is equal to b sub 0 plus b1 times x. It algebraically describes the equation of the line. Okay. Now, the regression equation expresses a relationship between x, which is going to be called the explanatory variable or the predictor variable, or in some cases, the independent variable. And then y hat is going to be called the response variable or the dependent variable. Okay, now the preceding definition shows that in statistics, the typical equation of a straight line, y equal mx plus b, which is used in algebra, that can be expressed in this form: y hat equals to b sub 0 plus b sub 1 times x. The b sub 0 is going to be the y-intercept. B sub 1 is your slope. And if you recall, the coefficient of your x term, when it's written in y equal mx plus b, the coefficient of your x term is your slope. And then the b is the y-intercept. Now, in this case, you'll notice that the y-intercept is written in front, and then the linear part, where the b sub 1 is going to be your slope. Okay. All right, now let's look at some notation here that we're going to be dealing with. Here, if you're dealing with the population parameter, they use Greek letters. So the y-intercept of the regression line would be b sub 0. The slope of the regression equation would be beta sub 1. And this equation of the regression line is y is equal to beta sub 0, that's the y-intercept, plus beta sub 1 times x, where beta sub 1 is your slope. Now for the sample statistic, the sample statistic is this. B sub 0 is your y-intercept, b sub 1 is the slope. And this is the equation, y hat equal to b sub 1 plus, b sub 0 plus b sub 1 times x. All right. So now if we look at the next page, here's example 1. And this is just pretty much a review of just what I got through talking about. In this case, what is the difference? What is the difference between the following two regression equations? The one on the left is y hat equals b sub 0 plus b sub 1 times x. And the second one is y is equal to beta sub 0 plus beta sub 1 times x. Notice on the left, that first equation is going to be for sample data. Okay. So the first equation, the one on the left, is for sample data. You'll be given paired sample data. And if you know what X is, you can easily pretty much find out what Y is going to be, or Y hat. But the one on the right is going to be for a population. Okay. So the second equation in this case is for a population. Okay. All right, now there's some requirements that we need to be familiar with. One is a sample of paired XY data is a simple random sample, meaning that samples of the same size have an equal chance of being selected. And number two, visual examination of the scatter plot shows that the points approximate a straight line pattern. And then number three, outliers can have a strong effect on the regression equation. So remove any outliers if they are known to be errors, and consider the effects of outliers that are not known errors. Okay. Here are the formulas for finding the slope and the y-intercept in the regression equation. Y hat equal to b sub 0 plus b sub 1 times x. To find the slope, I doubt if we'll use these formulas here, but the slope in this case would be b sub 1 equaling to r, which is the linear correlation coefficient, times s of y divided by s of x. S of y is the standard deviation of the y values. S of x is the standard deviation of the x values. You'll pretty much have to use technology to come up with the r and sy, s of y and s of s. And then for the y-intercept, that's going to be b sub 0 is equal to y bar, which is the mean of the y values, minus b sub 1 times x bar. Now the y bar is the mean of the y values. And if you recall, when you're finding the mean of the y values, you add the y coordinates together, divide by the number of y values that you have. And x bar, of course, is the mean of the x values. Again, you'll take the sum of your x values, divide that by n to get x bar. Okay. And in this case here, the slope, b1, and the y-intercept b sub 0 can be found using the following formulas that are useful for manual calculations or writing computer programs. And these are it. Okay. B sub 1, that's going to be equal to n times the sum of your x times y minus the sum of the x times the sum of the y, all divided by n times the sum of the x squares minus the square of the sum of your x's. I think we're going to be using this. Okay. And then for b sub 0, that's the sum of your y's times the sum of the x squared minus the sum of the x times the sum of the x times y's. And then that's divided by n times the sum of the x squared minus the sum of the x, whatever that sum is, you square it. Okay. All right, on the next page, for rounding b1 and b sub 0, you're going to round to 3 significant digits, or to 3 decimal places. Okay. And since we're not using the formulas 10-3 and 10-4, don't worry about that second bullet. But If you choose to use those two formulas, do not round your intermediate values. Okay. Now, here's how we use the regression equation for predictions. Number one, we use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. And then second, use the regression equation for predictions only if the linear correlation coefficient, which is your R, indicates that there is a linear correlation between the two variables. And then step three, use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. Predicting too far beyond the scope of the available sample data is called extrapolation, and it could result in bad predictions. And then number four, if the regression equation does not appear to be useful for making decisions, the best predicted value of a variable is its point estimate. And that point estimate is going to be the sample mean. Okay. And I need to change this to 10-1. Number two. Okay. Now here's a flow chart for predicting values of Y. Or strategy. You want to ask yourself, is the regression equation a good model? And the regression line graphed in the scatter plot shows that the line fits the points well. And R indicates that there is a linear correlation. The prediction is not much beyond the scope of the available sample data. Okay, if it is a good model, which is yes, then you go ahead and substitute your given value of X into the regression equation of Y hat is equal to B sub 0 plus B sub 1 times X. If it's not, then regardless of the value of X, the best predicted value of Y is going to be the value of Y bar, and that is the mean of the Y values, okay? So in this case, if that regression equation is not going to be a good model, then you have to take the average of your Y values in that raw data set. And that will give you the best predicted value of Y, regardless of what X is. All right, in summary, if we want the equation of the regression line, we're going to do these four things. And I do have a couple of examples where we will apply these four steps. Number one, you want to find the slope, which is your B1. And we're going to be using this. B1 is equal to N times the summation of X times Y minus the sum of your X times the sum of the Y. All that will be divided by N times the sum of the X squared minus the sum of the X, and that sum will be squared. That's step number one. Now, step number two is to evaluate X bar and Y bar. That's the mean of your X values and the mean of the Y values. Here, Y bar is going to be the sum of the Y divided by N, and X bar is going to be the sum of the X divided by N. And then step number three, find the Y-intercept, which is B sub 0. We're going to be using B sub 0 is equal to Y bar minus B sub 1 times X, because you have to do steps 1 and 2 in order to get to step number 3. Once you have your slope and your Y-intercept, the fourth step would be to substitute B1 and B sub 0 in the regression equation, which is your Y hat equal to B sub 0 plus B sub 1 times X. Okay. All right, now on the next page is to determine if a regression equation is a good model. We're going to start by using the 8-step procedure for hypothesis testing. So you might need to look through your notes from Chapter 8 and Chapter 9, that 8-step procedure that we've been using. And you're going to calculate R as the test statistic. And then number 2, determine if there is sufficient evidence to conclude that there is a linear correlation. And if there is sufficient evidence of a linear correlation, then the regression equation is a good model. And you just go ahead and substitute the given value of X into the regression equation. However, if there is no sufficient evidence of a linear correlation, then the best predicted value of Y hat is the value of Y bar. And that's the mean of the Y values. Okay. All right, now let's take a look at example 2. And that's this. Suppose IQ scores were obtained for 20 randomly selected sets of couples. The 20 pairs of measurements yield X bar is equal to 100.95, Y bar is 102.2, R is equal to 0.940, the p-value is 0.000, and Y hat is equal to negative 5.14 plus 1.06x. And this is where X represents the IQ score of the husband. Find the best predicted Y value of Y hat, given that the husband has an IQ of 109. And you want to use a significance level of 0.05. So we are going to be using a hypothesis test procedure for this. And of course, if you recall, the very first step is the original claim. And we're testing the claim to determine if there is a linear correlation between the two. Okay, so that means that rho is not equal to 0. And then step number 2 is the opposite of the original claim. In this case, rho equals to 0. Not equal to and equal to are opposites. And then step number 3 is the null and the alternative hypothesis. Well, the null always has the equal sign, so that means that rho is equal to 0 is your null hypothesis. The alternative has either greater than, not equal to, or less than. So it'd be rho not equal to 0. And that is the claim, as well as the alternative hypothesis. Step number 4 is the level of significance. And that's given as 0.05. You're told to use a significance level of 0.05. Okay, excuse me. All right, next is step number 5, your test statistic. Well, if you look in the problem, you're already given the test statistic, which is the linear correlation coefficient, that's R, equaling the 0.940. And step number 6, you're also given the p-value. That's 0.000. Well, the p-value is a really small number, so they only rounded to 3 decimal places to get for this. All right, step number 7 is the decision rule. And since we're given the p-value, we need to compare the p-value with our level of significance here. So here, if the p-value is less than or equal to alpha, your level of significance, you'll reject the null hypothesis. So the p-value, 0.000, and your alpha level is 0.05. Compare those two, you'll see 0.000 is less than 0.05. So that means we will reject the null hypothesis because it does satisfy our decision rule. So here we reject the null hypothesis. And then step number 8 is this. We rejected the null. The claim was the alternative. So that means that there is sufficient evidence to support the claim. That means we can say here there is sufficient evidence to support the claim. That there is and I'll just say linear correlation. And that's all I'll say about that right there. Okay. Now, since there is sufficient evidence that there is a linear correlation, I can find out the best predicted value of y hat. Okay. So in this case here, we'll find the best predicted value for y hat, or the best predicted value of y hat. And we're given that the husband has an IQ score of 109. So that means X will have to be equal to 109. Then we'll let X represent the IQ score of the husband. Okay. And our linear correlation, or our regression equation, is this. Y is equal to negative 5.14 plus 1.06x. That's our regression equation. So we just substitute the x with 109. So we got y hat is equal to negative 5.14 plus 1.06 times x, which is 109. And in this case, let's see, negative 5.14 plus 1.06 times 109. Then hit enter. And if you were to round this off to 2 decimal places, that would have to be 110.40. So y hat is equal to 110.4. And then I had to put a 0 behind it because it might say round to 2 decimal places. So that 110.40 will be the best predicted value of y hat when, and we're given that the husband has the high IQ score of 109. Okay, let's look at example 3. Remember that 4-step procedure that I gave you for finding the equation of a regression line? That's what we're going to do in examples 3 and 4. Here we're going to use the given data to find the equation of the regression line. And we're going to round the final values to 3 significant digits if necessary. So here is my paired XY data. I only have like 5 paired data. All right, this is what I'm going to do here. I'm going to extend this table just a little bit, because I'm going to need to find 2 things, x squared and x times y. Because in that regression equation, well, in that equation for B1, it does have, I know, the sum of the xy's and the sum of the x squares. and I'm going to need the sum of the x and the y. Okay, let's find the sum of the x. And that's just simply adding all the x coordinates together, 6 plus 8 plus 20 plus 28 plus 36. And that would give you 98. So out to the side, I would say the sum of the x is 98. And then I need the sum of the y values here. That's these numbers down here, the 2, the 4, 13, 20, and 30. So 2 plus 4 plus 13 plus 20 plus 30. That would give me 69. So the sum of the y's will be 69. And I'm also going to write out to the side that n, that's the number of paired data, is 5. I got 1, 2, 3, 4, 5 pairs of XY data. And now I'm going to square the x's. I'm going to take each x value and square it. So 6 and u squared is like 6 times 6. That's 36. The 8 squared is 8 times 8, that's 64. 20 squared is 20 times 20, which is 400. 28 squared is 28 times 28, which is 784. And finally, 36 squared, 36 times 36, that'd be 1,296. And I'll go ahead and get the sum of the x squares. So in this case here, if I add 36, 64, 400, 784, and 1296. That'd be 2,580. So the sum of the x squares is 2,580. And then for xy, x times y, that means I multiply the x and the y values together. 6 times 2, that's 12. And then 8 times 4, that's 32. And then 20 times 13, that will be 260. 28 times 20, that would be 560. And then 36 times 30, that's 1,080. So now the sum of the x times y, we do 12 times 32 times 260 times 560 times 1,080. That'd be 1,944. So the sum of the x times y's will be 1,944. So this is what's going to help me, in this case, find B1. And B1 is this: n times the sum of your x times y minus the sum of the x times the sum of the y, that's the numerator, all divided by n times the sum of the x squared minus the square of the sum of the x. So we're going to substitute all of these values into this formula here for B1. Your n is 5, so that's going to be 5 times the sum of the xy, that's 1,944, minus the sum of the x, that's 98, times the sum of the y, that's 69, all divided by the denominator, that's going to be n, which is 5, times the sum of the x squared. The sum of the x squared was 2,580, minus the sum of the x was 98, but that's going to be squared, so this will be 98 squared. And I think we could do all of this in the calculator by putting parentheses in the numerator and in the denominator. Let's see what happens. So here, left parentheses, 5 times 1944 minus 98 times 69. We can close the parentheses. Now this calculator does do the order of operations. And then divided by the denominator left parentheses 5 times 2,580 minus 98, and then that's going to be squared. Close parentheses. And then we hit enter. Okay, I made a mistake. That should be a minus sign in the denominator. This right here should be minus. Okay. Let's see, that works. Yeah, that works. So here, I'm going to try to use as many decimal places as I can here. This will be 0.89745. Okay. So that's what B1 is, 0.89745. So that's how we find B1. Now, X bar and Y bar are going to be easy because X bar, that's the mean of your X values. That will be the sum of all of your X's. The sum of all the X's divided by N, the number of X values that you have. The sum of the X's was 98. That's going to be divided by 5 because N is equal to 5. So 98 divided by 5, that'd be 19.6. That's what X bar is equal to. And Y bar is the sum of the Y values divided by N. The sum of the Y's was 69. And N was 5. So 69 divided by 5 ends up as 13.8. Okay. Now we're going to find out what that Y-intercept is, B sub 0. And that's equal to Y bar minus B sub 1 times X bar. So the Y bar was 13.8 minus B1, that's 0.89745. Let me put a 0 in front because that is a decimal less than 1. 0.89745. That'd be multiplied by what X bar is, in this case, 19.6. Okay, so if I type all this in, 13.8 minus 0.89745 times 19.6, I will get a negative 3.79. And I'm going to round that off to 2 decimal places. All right. So to write my regression equation, that's of course Y hat is equal to B sub 0 plus B sub 1 times X. I know what B sub 1 is and I know what B sub 0 is. All I have to do there is just substitute. So I'm going to have Y hat is equal to B sub 0 is negative 3.79 plus B sub 1. Here I can round to 3 decimal places. So this will be 0.897, 0.897 times X. This represents the regression equation for this data set. Okay. All right, let's do another problem like that. here we got the given data. We're going to use that to find the equation of the regression line. So here we're going to round the final values to 3 significant digits if necessary. Okay, so here's our data set here. And there are 5 paired data. So I know what n is going to be equal to. It's going to be 5. Let's go ahead and find the sum of the x and the sum of the y. The sum of the x coordinates here, that's just 1 plus 3 plus 5 plus 7 plus 9. That would be 25. So the sum of the x's is 25. And the sum of the y's, this will be 143 plus 116 plus 100 plus 98 plus 90. That would give me 547. So the sum of the y's is 547. Okay. Okay. Now I need the sum of the x squares and the sum of the x times y. So I'm going to extend this table out a bit. So here I'm going to have an x squared and x times y. So all I'm going to do is square each individual x value. So 1 squared, or 1 times 1 will be 1. 3 squared, or 3 times 3 is 9. 5 squared, 5 times 5 is 25. 7 squared, or 7 times 7 would be 49. And 9 squared, or 9 times 9 is 81. And then I'll take the sum of the x squares. So in this case, if I add 1 plus 9 plus 25 plus 49 plus 81, that would be 165. So the sum of the x squares is 165. Okay. And now I need to do x times y. That means I need to multiply the x and the y values together. So 1 times 143 is 143. And then 3 times 116 would be 348. And then 5 times 100 would be 500. 7 times 98 would be 686. And then finally, 9 times 90 would be 810. So this will give me the sum. So I need to find the sum of the x times y values. So we add 143 plus 348 plus 500 plus 686 plus 810. This will give me 2,487. Okay. So now the first thing I need to do there is find D1, which is, of course, my slope for the regression equation. And that's, of course, is n times the sum of the x times y minus the sum of the x times the sum of the y divided by n times the sum of the x squared minus the sum of the x, and that's going to be squared. Okay. And of course, our n, there are 5 paired data, so n would be equal to 5. All right, so n is 5, we just substitute, times the sum of the x times y. That's 2,487. Minus the sum of the x is 25, times the sum of the y, that's 547. And that whole thing will be divided by n, again, that's going to be 5, times the sum of the x squared. Is the sum of the x squared, that's 165. Minus the sum of the x, that's 25. And that 25 has to be squared. Okay. in the meantime, I'll put these in parentheses. And if we use our calculator, left parentheses, 5 times 2487 minus 25 times 547, close parentheses, divided by, and then left parentheses, 5 times 165 minus 25, and then square it, close parentheses. Then hit enter. So here I got a negative for the B1, and that's going to be negative 6.2. Okay. So that tells me my slope is going to be negative. That means that the regression line will be decreasing. And I should know that because as my X values increase here, my Y values are decreasing. So I know I'm going to have a negative slope. And now I need the mean of the X and the Y values here. Your mean, X bar, that's the sum of the X divided by N. The sum of the X's was 25. And N was 5. So 25 divided by 5 will end up being 5. And then Y bar is the sum of the Y values, all divided by N. The sum of those Y values was 547 divided by N, which is 5. So 547 divided by 5, that will end up being 109.4. All right. So I'm going to use that to find out what my Y-intercept is, and that is B sub 0. That's the third step there. B sub 0 is this, Y bar minus B sub 1 times X bar. My Y bar, which is the mean of the Y values, that's 109.4, minus B sub 1, which was the slope, and that's negative 6.2, times X bar, that's 5. So here we go, 109.4 minus, and I'm going to put negative 6.2 in parentheses. The negative key is at the very bottom of the calculator, so you press that key, and then 6.2, close parentheses, times 5, and then hit enter. And you'll get 140.4. Now, if you wanted to, you could make that minus a negative 6.2 a plus, and you'll still get 140.4. Now, let's find out what our regression equation is going to be. We use y hat is equal to b sub 0 plus b sub 1 times x, and just substitute. So bring down the y hat, that's equal to b sub 0, that's 140.4, plus b sub 1, that's negative 6.2 times x. And another way you can write that is just say y hat is equal to 140.4 minus 6.2 times x. And this will be the regression equation for this data set. Okay. All right, now in the last two examples, we won't have to go through this procedure that I just did here. We can use our graphing calculator to come up with the equation of the regression line, and I'll be showing you that shortly. Okay. So here's example 5. It says that the data shows the chest size and weights of several bears. Find the regression equation, letting the chest size be the independent x variable. Then find the best predicted weight of a bear with a chest size of 63 inches. Is the result close to the actual weight of 562 pounds? Use a significance level of 0.05. Okay, we'll start by finding the regression equation. And we're going to use our TI-83 or 84 plus graphing calculator. So using a TI-84 plus calculator. Now, if you recall back in the last video for section 10-1, I showed you how to enter data into list 1 and list 2. Okay, so in this case here, go to stats, and we're going to edit because we're going to be putting in brand new data values. So we select number 1. And to clear any data that you have here, let's do this. Use your up arrow key to highlight L1 in this case, press clear and enter. And then for L2, use your up arrow key to highlight L2, press clear, enter. That clears out all the data. All right, the chest size in inch will go into L1. So in this case here we have 58, then 50, 65, 59, another 59, and 48. And then we use our right arrow key to enter the weight in L2. So in this case here, that's 414, then 312, 499, 450, 456, and 260. And make sure that you press enter even after the last number. And make sure your data values are correct and you have the same number of data values in L1 as you do for L2. All right, so here's how we're going to get that regression equation. Press the stat key. Right arrow one time to calculate to the calculate menu. Now, as you're going to see this menu item that says lin reg AX plus B. Choose that. Lin reg AX plus B. That's the one you will choose. And then hit enter. Now, in this case here, your X list is L1, Y list is L2, frequency list, we leave that blank. This we don't worry about. We only go down to calculate. And again, you want to make sure your X list says L1. If it doesn't, then you have to do second and number 1 for L1. And if Y list says something else but L2, you want to make that L2 by doing second and number 2 to make it L2. Highlight calculate using your cursor, calculate. Now, it's going to give it to you in the form of Y equal AX plus B. So let me write it out as is, Y equal AX plus B. And then we just substitute the A and the B to 3 decimal place, well, to 1 decimal place for the Y. For the A, it'll be 14.3 to 1 decimal place. So that'll be 14.3 times X plus B is at negative 411.7. Okay. But of course, the regression equation is written in a way so that the Y-intercept is in front and the linear term is second. So here's your Y-intercept. That's going to be in front, that negative 411.7. And then plus the 14.3x would be behind it. Okay. And you have to write in this form. Otherwise, my MATLAB will count it incorrect. So you want to make sure that the Y-intercept, which is your constant term, that's in front, and then the linear term is behind it. That's the term with the coefficient of x in front. So that's your regression equation. Y hat is equal to negative 411.7 plus 14.3x. Now we're going to find out if this equation is a equation that is a good fit. And you have to do that by doing the hypothesis testing procedure. Okay. We want to find out, is this equation a good model? So in this case here, step number one is the original claim. So we're testing the claim that there is a linear correlation between these two variables here. So the original claim would be rho is not equal to 0, meaning that there is a linear correlation. And then step number two is the opposite of the original claim. So that means rho is equal to 0, meaning that there is no linear correlation between the two. Step number three is writing out null and alternative hypothesis. Okay, and this is it. The null always has the equal sign. The alternative does not. Okay. And then step number 5, you're told to use a significance level of 0.05. So in step number 4, alpha is equal to 0.05. Now, step number 5 is calculating the test statistic. In this case, I'm going to be using the TI-84 plus calculator. So I'm going to find out what R is. And to do that, we press stat. This time we go up to test using the right arrow key. We're going to go down using the down arrow key to the menu item, linreg t-test. Here it is, linreg t-test. So here we're going to press enter. X list should always be L1. So you might have to do second and number 1 for L1. The Y list should always be L2. So you might have to do second and L2 for that. Frequency is still going to be 1. Not equal to 0 is always going to be highlighted because our alternative hypothesis says that rho is not equal to 0. And we'll get rid of that and then calculate. So we press enter. Let's find out what R is going to be using this down arrow key, because that tells us that there's more stuff down there on that screen. So here's your R, which is to 3 decimal places, 0.982. So our linear correlation coefficient is going to be 0.982. Now, step number 6, I'm going to use the TI-84 plus calculator to find the p-value. Because it is given on this screen and in this output. So here, if I use my up arrow key, notice that p-value is a very small number, 4.802, and that's times 10 to the negative 4. And that is in scientific notation. So let me show you how this is done. I'll just say 4.802. and that's times 10 to the negative 4. To write in standard notation, I need to move this decimal point 4 places to the left because it's negative 4. So it'll be 1, 2, 3, 4. And I need 3 zeros in front of that. So that's going to be 0.0004802. And then I'll follow it with the rest of the numbers. But this is all I need because I'm going to round this up to 3 decimal places. This third 0 is in the third decimal place. The right of it is a 4, it's less than 5. So I'm going to have 0.000. So that p-value is very small. So my p-value is 0.000. And now step number 7 is the decision rule. Comparing the p-value with my level of significance. And if the p-value is less than or equal to alpha, you want to reject the null hypothesis. Less than or equal to alpha for the p-value, you reject the null hypothesis. The p-value was 0.000. The alpha level was 0.05. And of course, definitely 0.000 is less than 0.05. That means we need to reject the null hypothesis. And if we reject the null hypothesis, that's going to mean, in this case, well, we rejected the null. The claim was the alternative. That means that there is sufficient evidence to support the claim. That means that there is sufficient evidence to support the claim that there is a linear correlation between chest size and weights and weight. Now, since there is sufficient evidence to support the claim, that means we can find out what the best predicted weight is going to be. Okay? And it says here, we want the best predicted weight of a bear with a chest size of 63 inches. So in this case here, we use that regression equation that we came up with. That's y hat is equal to negative 4, 11.7 plus 14.3 times x. And x is 63, so here y hat is equal to negative 4, 11.7 plus 14.3 times 63. So just simplify that. So in this case, clear this out. Negative 411.7 plus 14.3 times 63. And here we're going to get 489.2, which is the best predicted weight of a bear with the chest size of 63 inches. Now, is the result close to the actual weight of 562 pounds? And the answer there is definitely no. So here we can just say that the result is not. Very close to the actual weight of the bear. Okay. Okay, and we'll do one more of these, and this is the last one in this video. The data shows the bug chirps per minute at different temperatures. Find the regression equation, letting the first variable be the independent x variable. Find the best predicted temperature for a time when a bug is chirping at the rate of 3,000 chirps per minute. Use a significance level of 0.05. What's wrong with this predicted value? Okay, so here's the table. The first row, chirps per minute in 1 minute, and then the temperature in degrees Fahrenheit is the second row. So let's find out what that regression equation is going to be. And here we're going to be using the TI 84 plus calculator. And again, you can also do this on the TI 83 if you like. Let's see, press the stack key. We're going to edit, so we're going to select number 1 for edit. Let's clear these data values out. So do up arrow to highlight L1, clear, enter. Go to L2, up arrow to highlight L2, clear, enter. And let's enter the chirps in 1 minute in L1. So this will be 1224, 758, 862, 1057, 1076, and 1068. And then use your right arrow key to go over to L2. Enter the temperatures in L2. So it'll be 94.6. Let me see, 69, 73.2, 78.5, 80.1, and finally 87. Okay, make sure your data values are correct, and also make sure that the same number of data values in L1 are the same as the ones for L2. Okay, so now next step would be to go to Stat, press the Stat key, and then use your right arrow key to go over to Calculate, and then go down to linreg AX plus B. Hit Enter. X list should still be L1, Y list should still be L2. Frequency list, don't worry about that. The store, don't worry about that. Just go down and calculate. Put the cursor on top of calculate and press enter. So here, it gives you in the form of y equal ax plus b. So let me write that in. So here, y is equal to, the a is the coefficient of x. Let's see, in well, they're using 4 decimal places, so this will be 0.0514. And that's the coefficient of your x plus the b, and they're using 28.62 to 2 decimal places. Okay, but they had the y-intercept in front. So this 28.62, that's your y-intercept, that goes in front. And the linear term behind it. So this is your linear regression equation. Y hat is equal to 28.62 plus 0.0514x. All right. Now, let's do the 8-step hypothesis testing procedure to find out if this regression equation is a good model for this data set. Starting with step number 1, writing the original claim in symbolic form. And of course, our claim is going to be if there is a linear correlation between the two variables. So that means rho is not equal to 0. Step number 2 is the opposite of the original claim. And that's just going to be rho is equal to 0. Not equal to, its opposite is equal to. Step number 3 is to identify the null and the alternative hypothesis from steps 1 and 2. The null has the equal sign, that's rho is equal to 0. The alternative has the not equal to, so that's rho is not equal to 0. And that's also going to be your claim. Now, step number 4 is your level of significance. And you're told to use a 0.05 level of significance in this problem. So alpha is equal to 0.05. Now, step number 5, that's where we'll use our TI-84 or 83 plus calculator to come up with our linear correlation coefficient, which is, of course, R. And the way we do that is press the stat key, right arrow to test, use your down arrow key to find linreg t-test. Linreg t-test is what we want. Press enter. X list should still be L1, while this should still be L2. The not equal to 0 should always be highlighted because that's the only alternative hypothesis that we've been using for correlation and regression. And then press highlight, put calculate, put the cursor over calculate, and then press enter. And of course, I use my down arrow key to find out what R is. And here's what R is equal to. That's my linear correlation coefficient. To 3 decimal places, it will be 0.930. Okay. And I'm also going to use the TI-84 plus calculator to get the p-value. Okay. So if I use my up arrow key, here's the p-value, which is lowercase p. To 3 decimal places, that would be 0.007. That's my p-value, 0.007. Now, step number 7 is my decision rule. If this p-value is less than or equal to my level of significance, which is alpha, reject the null hypothesis. So here the p-value, we found that out to be 0.007. And the alpha level of significance is 0.05. Compare those two, you'll see that 0.007 is less than 0.05. So here we can reject the null hypothesis because it does satisfy the decision rule. Reject the null hypothesis. And then step number 8 is our conclusion using simple non-technical terms. the claim was the alternative, we rejected the null hypothesis. So that means that there is sufficient evidence to support the claim. So our conclusion statement would be this, that there is sufficient evidence to support the claim. That there is a linear correlation between chirps and temperature. Okay. Now, since there is sufficient evidence to support the claim, that means our regression equation is a good fit. That way we can find the best predicted temperature. Okay, so next we'll find the best predicted temperature. And that's for a time when a bug is chirping at the rate of 3,000 chirps per minute. So X is 3,000. Our regression equation was Y hat is equal to 28.62 plus 0.0514 times X. So we would just substitute the X with 3,000. So the Y hat is equal to 28.62 plus 0.0514 times 3,000. So in this case here, punching this into the calculator, 28.62 plus 0.0514 times 3,000. And this will give you 182.8 if you round this off to one decimal place. Now, if you look at this, the best predicted temperature for a time when a bug is chirping at the rate of 3,000 chirps per minute is 182.8 degrees Fahrenheit. Oh, that's something wrong with that problem. With that best predicted value, 182 degrees. That is unrealistically high. I don't know of any temperature in this world or in this country or anywhere where the temperature is 182.8 degrees Fahrenheit. Okay. So to answer that question, it is unrealistically high. Here, the value of 3,000 is far outside of the range of observed values. Okay. Far outside. Because if you look at your data set, I'm going to bring this down just a bit. Notice that your data values, the smallest is 758, and the largest in this case is 1,224. So you can see here that 3,000 is way outside those observed values. And that temperature would be unrealistically high. Okay. Now, I do want to mention here, if I failed to reject the null hypothesis here, then that would mean that there's not sufficient evidence to support the claim that there is a linear correlation. Now, if there wasn't sufficient evidence that there was a linear correlation, then that means we only take the average of our temperatures here in this case. I had to take the average of these, add these six numbers, six temperatures, and divide by 6. And that will tell me what Y bar is. And that Y bar will be used as the best predicted value for a bug chirping at 3,000 chirps per minute. Okay. Okay, so that's all I have here, and that will end this video on section 10-2 dealing with regression. Do feel free to email me or contact me. Well, just contact me if you have any questions regarding what was presented in this video, and also if you have questions on the homework in my math lab on section 10-2 regression.